Find the volume using cylindrical coordinates of the solid E, whose boundaries are given in rectangular coordinates. Number 258 says E is below the plane z equals 1, and inside the paraboloid, z equals x squared plus y squared. So let's just take a look at where x is 0. We're just going to try to do some traces here. And this is going to give me z equals y squared. So this is actually a parabola. So now keep in mind here, if x is 0, that means I will be here on the YZ plane. So that would be the parabola we see. So now let's take another trace here, and we're going to do the trace y equals 0. And that's going to give us the plane xz. And now we're going to do a parabola that way, because notice what we get when y is 0. So that goes away. So I'm going to get z equals x squared. So that would be that parabola. So that's going to give us then, so we can see the paraboloid forming there. And also with the plane z equals 1, I chopped it right at the 1 here, because that goes out here at 1. And that's what I wanted you to see with this picture. So it's really just that piece right there that we see. And that's what we have to find the volume of. And we're going to use cylindrical coordinates to do this. So here are those cylindrical coordinates. So that tells us then that if we're going to look at this x and this y, that when I look at this paraboloid here, I can see x squared plus y squared, and I have an x squared plus y squared here. So what I can say right away is x squared plus y squared equals r squared. And I know my z equals, or I'm sorry, not z squared, but z equals x squared plus y squared. So this tells me then that z equals r squared. And then for the other equation, this one here, the z equals 1, my z equals z. So that tells me z equals 1. So now we have all the parameters we need for this. There's one more thing we're missing here, because we're thinking about this in terms of a triple integral. So our setup will be, I have this triple integral, and then I have my 1, because the 1 is going to be, because we're talking about a volume, and a triple integral is going to give me a volume if my fxyz is 1. And then I have my Jacobian, and my Jacobian is going to be r theta z, and then I'm going to have dz, dr, d theta. So then for z goes up to down here, and it's going up to the 1. So if you look at the lower function, that lower function would actually be that paraboloid. It would be this one here, which is actually this equation here. So that's where the bottom bound then for z would be r squared. So that's going to be r squared here. And then the upper bound for it would be where z equals 1. It would be that plane. So then my z is going to go from r squared to 1. Now for r here, we have to understand the equation. So the equation being, we have z equals x squared plus y squared, and we also have z equals 1. So if I sub 1 into the other one, I get 1 equals x squared plus y squared, and x squared plus y squared is r squared. So r squared equals 1, which tells me r equals 1. So as far as the radius is concerned, it's going to run from 0 out to the function, and that function is going to be 1. It's going to go out as far as 1. So that's going to be from 0 to 1. Because we're always starting from 0 with those, unless we have a hole in the middle of our volume there. But since there's not a hole in the middle of volume, it's starting from 0 and going to 1. Okay, let's talk about theta now. Theta is easier to think about. So if my radius comes out, theta is going to have to take it all the way around. So theta is from 0 to 2 pi. So there's all of our bounds for this triple integral now. Now we just have to find the Jacobian. So that means we're going to need some room, but I'm going to save the triple integral. So then Jacobian, r theta z, is going to be this here, dx, dr, dx d theta, dx dz. And when we run through all of these partial derivatives with our transformation here, we're going to get, for the first one, dx dr is going to be just cosine theta because the derivative of r is cos theta. And dx d theta is going to be negative r sine theta. And then dx dz, there's no z there, so that's all a constant, so it's 0. Now I'm just going to fill in the rest of these. So remember, we can pick any row or any column. So I'm going to pick the bottom row here to be my top row in a sense. So I'm going to take the derivative of the, not derivative. So I'm going to take the first one here and then the determinant of this here. But since this is 0, I'm just going to get 0 times that, whatever that gives me. And that's just going to be a 0 there. So that's going to be 0. And the middle one I'm going to have to negate. So I'll take this one and this piece here and this piece over here. And that determinant is also going to be 0 because I'm timesing by 0. So the negation doesn't matter there. So I'm going to pick the last one now. And then it's going to be the derivative, not the derivative, the determinant of this one here. So that's what we're left with. So this is going to be 1 times, and then r times cosine is going to be r cosine squared theta. And then minus, but see I have a negative here and a positive there, so that's going to be a negative. So that's going to turn out to be a plus then. And that's going to be r sine squared theta. So then this cleans up to, the 1's just going to be 1. So I'm going to factor an r out of these two on the inside. So that's going to be an r, and I'm going to end up with cosine squared theta plus sine squared theta. And that cosine squared theta plus sine squared theta equals 1. So I get 1 times r, which is just r. So the Jacobian for the cylindrical coordinates is going to be r. So we're going to clean this up here, and I'm just going to write my Jacobian down. And when we look at the formula for that one, for the cylindrical coordinates, we'll see that this is what we end up with here. So this says, suppose that g, x, y, z is continuous on a rectangular box, which when described in cylindrical coordinates looks like b. R is from a to b, theta is from alpha to beta, and z is from c to d. Then the gxyz equals r cos theta, r sine theta z, which equals fr theta z. And check out this integral here. So we have this integral here that equals, now remember, our fr theta z is 1 because we're talking about a volume here. And that's 3 dimensions with the 3 integrals. And now notice this. They got an r right here. And that r is the r we have here. That's going to go right where this Jacobian's at. So what's interesting about this, without them even saying it, this r is the Jacobian of the cylindrical coordinates. And that's why we see r, dr, d theta, dz. And ours, we're doing the dz first, and it doesn't matter either way. I'm doing the dz first because dz is reliant on r, and r is reliant on dz. So I'm going to do it that way for that reason. So since I have z being equal to r squared and z equaling 1, I'm just going to do that one first. So then I don't have to do any converting or anything like that. And it's just very straightforward. So it just makes it a little easier to run through the computation and without even changing it or with less hassle. So we're going to work through the integral now, and I wanted you to see that from the theorem in cylindrical coordinates in section 5.5. So let's get started. So this is still the triple integral from 0 to 2 pi, still from 0 to 1. And now in place of this Jacobian here, we can put our r. So it's going to be r squared and then to 1. And then we're going to have r dz dr d theta. And then when I do my first integral here, it's going to be 0 to 2 pi, 0 to 1, and then this, oops, can't have an equal there yet. This is going to be rz, and that's going to be from r squared to 1, and then dr d theta. So then this is going to equal 0 to 2 pi, integral from 0 to 1, and my upper bound, I'm going to plug in the 1 for the z, so I'm going to have an r here, and minus the lower bound, which when I plug a r squared in there, that's going to make it r cubed, and that's going to be dr d theta. Now to integrate r minus r cubed, that's just a simple power rule. So this is going to be the integral from 0 to 2 pi. I haven't touched that one yet. And this is going to be 1/2 r squared minus 1/4 r to the 4. And that's going to be from 0 to 1. And then I'll have to do d theta. So then when I plug that in, the upper bound is going to give me 1 for those r's. And the lower bound is going to give me zeros, which means I'm just going to be subtracting a 0 for the lower bound. So this is going to end up being the integral from 0 to 2 pi. 1/2 times 1 squared is 1/2. Minus 1 to the 4th times 1/4 is going to be minus 1/4. And then like I said, when I plug in the lower bound, it's going to be minus a 0. So I'm not going to worry about it. And that's going to be d theta. And I can put those together now. 1/2 minus 1/4 is 1/4. So that's going to be the integral from 0 to 2 pi of 1/4 d theta. So then to finish this problem, this is going to be 1/4 from 1/4 theta from 0 to 2 pi. So it's going to be 1/4 times 2 pi, so 2 pi fourths minus the 0 there, which I don't have to worry about when I plug in the lower bound, and that's going to equal pi halves. So there's our answer. And with this problem, I wanted to go through the Jacobian for you so you could see where in their formula they have that you can see where that r comes from. It's actually just the Jacobian. So there's our answer.